Let us look at proposition number 9 of book 13 of Euclid's Elements. The proposition says, if the side of the hexagon and that of the decagon inscribed in the same circle are added together, then the whole straight line has been cut in extreme and mean ratio, and its greater segment is the side of the hexagon. So, let's see what this means and how to prove it. Let ABC be a circle with inscribed hexagon and decagon. So let's inscribe a decagon and let's inscribe a hexagon. BC is the side of the decagon. So let's mark this as B and this as C. BP is the side of the hexagon. So let's say this is P. So BP is the side of the hexagon. BC is the side of the decagon. Extend BC so that, let's mark this as D, CD is equal to BP. Now what the proposition is saying is that BD has been cut in the extreme and mean ratio at C, and CD is the greater segment. So let's take it step by step. Find the center of the circle E and draw EC and ED. Mark the intersection of the circle ABC and ED as F. Draw BE and extend it to A. So B, extend it to A. So let's mark this as A. Circumference ACB is equal to 5 times the circumference BC. Why? Because the entire circumference of this circle has been inscribed with the decagon, and BC is the side of the decagon. So in a semicircle, 5 of these sides will be present. So circumference ACB is equal to 5 times circumference BC. Circumference AC will be equal to 4 times BC. So which means circumference AC is to circumference BC as angle AEC. Angle AEC is to angle BEC. So that means angle AEC will also be 4 times the angle BEC. Angle CBE is equal to angle BCE. Since BE is equal to C, they are the radii of the same circle. Angle AEC is the external angle to the triangle BCE. And these, so which means it is external angle will be the sum of the interior opposite angles. And these two angles are equal. So we can say angle AEC is equal to 2 times BCE. EC is equal to CD, since both are equal to the side of the hexagon. So that means angle CED is equal to angle CBE. Angle AEC is equal to 2 times angle BCE. You have already seen this. But angle BCE is equal to 2 times angle CDE, because again angle BCE is the external angle. That means it is going to be equal to the sum of the interior opposite angles. That is angle CED and EDC. That would be equal to this. And these two are equal. So again, let's take it from the top. AEC is equal to 2 times BCE. But angle BCE is equal to 2 times CDE. That means angle AEC is equal to 4 times CDE. Yes. Now, AEC is equal to 4 times angle CDE, and angle AEC is equal to 4 times BEC. So we can say CDE is equal to BEC, since both are 1/4 of angle AEC. Triangle EBD is equiangular with triangle EBC, since EBD angle is common to both. CDE is equal to BEC, and since two angles are equal to two angles, that means the third angle also has to be equal, because the sum has to be 180 degrees. So proportionately we can say BD is to BE as BE is to BC. BD of this triangle is to BE of this triangle is equal to BE of this entire triangle is to BC of this triangle. So here BE is equal to CD. BE is equal to CD. In an inscribed hexagon, the side of the hexagon is equal to the radius of the circle. So which means we can substitute BE with CD here. So the proportionality becomes BD is to CD is equal to CD is to BC. And which means BD times BC is equal to CD square. Or more appropriately, the rectangle BD by BC is equal to the square on CD. Which means that BD has been cut at C in the extreme and mean ratio. And looking at this proportionality, since BD is greater than CD, that means CD will also be greater than BC, which is what we had to prove. So that is proposition number 9 of book 13 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.